Welcome back. This is video lecture 28.4, and there are two more sections in chapter 28 to talk about. The sections go together. We're starting with section 7 of chapter 28, where we're going to take current and in a wire and wrap that wire around some kind of a frame that's planar, flat. It might be rectangular shaped, it might be circularly shaped, it might be some even more complicated shape. But we've got current going around a frame and just going around and around and around. We call that a current loop. And we're going to immerse this loop of current in an external magnetic field, such as between the poles of a magnet. And we're going to mount this loop on an axis that can turn, like the axis of a wheel. And what we have ultimately is the heart, the essence of an electric motor, which is a very important piece of technology. There's no doubt about that. So it's worth understanding the physics of the basic operation of such a motor by looking at the tendency for a current loop in a magnetic field to rotate about this axis of rotation. And when we talk about rotation, about an axis, we tend in physics to talk about the concept of torque. So the key idea here is to calculate the torque on a current loop in an external magnetic field. And here's the device I want to talk about. It is, at its simplest level, an electric motor. All right, we have a conducting loop. You can see there it's shaped like a rectangle. It's got current I flowing around it. As we look at it from this perspective right now, that current is flowing around, I would call that counterclockwise. And it's been immersed in a uniform magnetic field. The diagram shows that it's been immersed between the poles of a magnet. And of course, every magnet has two poles, a north pole and a south pole. Okay? And the magnetic field points away from the north pole and towards the south pole. And given the orientation of the north and south poles here, the uniform magnetic field points from our left to right. And this current carrying loop is immersed in this uniform magnetic field. That's the device. Quite simple when you look at it in that sense, okay? Yet amazingly useful. Now, one of the key physics we just talked about is that if you have a current carrying wire in an external magnetic field, you can get a magnetic force on that wire. F sub B equals I times L cross B, L arrow cross B arrow. And that physics, which is not new to us now, is what's important here. For the leftmost side, as we look at this structure right there, we can apply I times L cross B. Notice what the L arrow would be for that left side. It would be like that. Do you see why? It's the length of that side, and it points in the direction of the current on that side. Now, of course, we know the direction of the B all along that side, like so, and you drew the right-hand rule and do L cross B, and sure enough, that's the direction of the force, magnetic force, that you'll get on that side. Upward, you might call that. Whereas the side opposite, which would have an L vector like that, would it not? But the same B, and you do the right-hand rule, and you will get an F magnetic downward. Okay, so those are two magnetic forces on the two long sides. Notice in this configuration, what's the magnetic force on each of the shorter sides? Did you say 0? And did you say 0 because the L vector and the B vector are either parallel or anti-parallel? You think about that, okay? Notice, too, that of these two forces that I do have on those two opposite sides of that loop, they will have equal magnitudes and they clearly have opposite directions. So the net force is 0, right? The net force on this loop is 0. So that means, from Newton, that the center of mass of this loop will not accelerate. However, I have an axis of rotation here, don't I? That's what this thing is. right here, here and here. It's mounted to some structure so that this loop can rotate. And I know that it will, because I can see that for the axis of rotation and those two forces together, there will be a net torque, tau arrow, about the axis. And our job here is to calculate that torque. Okay? Now, in order to do that calculation, we're going to have to draw this same device, pictures of it, from a number of different perspectives. And it's just going to be required because we're going to have to think three-dimensionally, and so for that we're going to need a number of different pictures. So the first thing I'm going to do is show you, well, the next thing I'm going to do is show you a picture that we would observe from the same device from a slightly different perspective. Now the perspective will be, I'll try to draw kind of a shape like an eye to show where we are and which way we're looking, as if we are inside the field region with our back up against the North Pole looking towards the South Pole. So the magnetic field vectors will be going directly away from us. And I'm going to assume that this structure has been rotated clockwise by 90 degrees. And when all of that happens, here's what the structure looks like. Same structure. Let me draw a little bit more of a sketch over here to the side, a kind of a perspective view, because it's important that you understand these pictures. All right, over here on the left is the North Pole of the magnet. Over here on the right is the South Pole. Here's where we are standing, looking to the right. We are standing with our back up against the North Pole, looking towards the South Pole. The magnetic field lines, magnetic field vectors, B, are pointing away from us towards the South Pole. And in that field, here is our structure, our loop. Here's the axis of rotation, right in the middle, here and here. And the current I is flowing up that side, over at the top, down in the front, and back this way at the bottom. Okay, that's my perspective view. So now, imagine what things would look like if you are right there looking in that direction. And what I contend is it would look like what we see now in the middle of the screen. Okay, we would see a rectangle. We would see conventional current flowing, I, counterclockwise around the loop. It never disappears. It doesn't dissipate. It's just going around and around and around. We've labeled the rectangle with four sides. Side 1 at the top, side 2 at our right, side 3 at the bottom, side 4 at our left. I've said the object is shaped like a rectangle. The long dimension is length little a, and the short dimension is length little b. And the magnetic field vectors are uniformly spaced and pointing into the screen. And it's kind of hard to see it, but the axis of rotation is coming out this way and this way. All right, so I want to look at that some more. And I want to draw the magnetic force vectors on the four sides. Okay? So I remind you that the physics for calculating the magnetic force on a current carrying wire, if it's a straight wire in a uniform magnetic field, important restrictions, is I times L cross B. So for example, for the top side, side 1, there's the L vector. And the B is into the screen. So take a moment, practice with the right-hand rule, do the two-pen approach. I'll use a red pen for L and a green pen for B. And as I'm looking at this, L points to my right and B points into the screen away from me. And I do L cross B, don't do it the other way around, don't do B cross L, that would be wrong. L cross B, with the right hand, your thumb points up. The magnetic force on this side 1, which I'll just call F1, is in the plane of the screen and upward. All right, now let me draw the L vector for side 2. It's that. The B is still into the screen. What's the direction of the magnetic force on side 2? Did you say to our right, like this? We'll call that F2. All right, now side 3, down here. There's the L vector. B again, into the screen. What's the direction of F3? Did you say straight down in the plane of the screen? And then lastly, for side 4, there's the L vector. B again, into the screen. What's the direction of F4? Did you say to our left in the plane of the screen? So there are the 4 forces. And because sides 1 and 4 have equal length, the magnitudes of these forces, F1 and F3, are equal, but they're clearly in opposite directions. So it's pretty clear that F1 vector plus F3 vector equals 0. And because sides 2 and 4 have equal length, the magnitude of F2 and the magnitude of F4 are equal, but they're in opposite directions. So when I add those force vectors, F2 plus F4, I also get 0. So once again, the net force is 0. But what I'm interested in is the torque. Now, it turns out in this particular orientation of the loop, remember the loop can rotate about an axis, so it doesn't necessarily always have to be found in this orientation. This orientation is just kind of helpful to get started looking at things. Turns out there is no tendency to rotate in this case. There is no torque in this particular orientation of the loop. But we'll change that in just a minute. I just want you to see how we're looking at these 4 sides, how we're looking at the current going around each side, thinking of an L vector for each side, figuring out what direction the B vector is, doing I times L cross B, and figuring out which way the magnetic forces are. Here's another idea that's useful when working with a current loop. Okay? And that's to introduce yet one more kind of vector, a normal vector. We've actually talked briefly about this kind of vector before. A normal unit vector n hat for a loop. Its characteristics are pretty easy to state. First of all, a unit vector has magnitude 1, it has no units, and its job is to merely point in a particular direction. So that's all we have to clarify. What is the direction for the unit vector, the normal unit vector, n hat, for a current loop? Here it is. The direction is perpendicular to the plane of the loop. So for this picture, the plane of the loop is the plane of the screen. So perpendicular to the loop means either directly out of the screen towards us or directly into the screen away from us. And how do we determine? What's the definition? It is in the direction of the outstretched thumb of the right hand when the fingers of the right hand are curled in the direction of the current. It's kind of a right-hand rule. You might call it a modified RHR. Right-hand rule. That's what's being described in words. So what you do is you take your right hand, stick out your thumb like you're hitchhiking, take the palm of your hand with your fingers and reach in with your fingers as if you were going to wrap them around the loop the way the current is flowing. And as I look at the screen here, the current's flowing clockwise, so I have to have my fingers curling clockwise. If I did this way, my fingers would be curling counterclockwise. This way, and then your thumb points in the direction of the n hat. My thumb points down. Down to me means into the screen. Okay? So the n hat vector for this loop in its current configuration, I would draw right in the center, and I would draw it as an X encircled, meaning that the arrow points into the screen. And that's the direction of the normal unit vector for this loop when it's oriented like we see it here. Okay? All right, now let's get down to the actual orientation picture that's going to help us calculate the torque. And it's going to be a little bit more like our perspective view, except now I'm going to change my perspective. So now look at my drawing up there. Now I'm going to change where my eye is, as it were. My eye is now kind of in the front, looking towards the loop. I call that a side view. And let's let the loop not be straight up and down in the magnetic field, but angled back a little bit. Okay, so now I'm looking from the front, so I'm seeing a side view, and the loop is now angled a little bit. It's not straight up and down. What it would look like then is this. Okay, here's a side view of the loop with the rotation axis coming out of the screen, rotated so that this new unit vector n hat, right there, has some angle theta to the direction of the magnetic field, B. There you can see the theta. That's the angle between n hat and B. And that theta, that n hat direction, comes from this modified right-hand rule. You reach with your right hand in, around to grasp hold of the loop, with your fingers curling around the loop the way the current flows. And the n hat has to be perpendicular to the plane of the loop. All right, now, I want to describe what's going on with each of the four sides. Same four sides, 1, 2, 3, and 4, like we talked about in the previous picture. But let's be clear what's happening with each of those sides. For example, side number 1. Okay, it has current I flowing in it, and its L vector, which would go along that length, 1, of side 1, but pointing in the direction of the current, that L vector is directed out of the screen towards us. Okay? And when we do I times L cross B, the B is now going to the right, we get a force on that side that is vertically up. Notice that's labeled F1. Force on side 1. All right, notice the label here, side 2. It's right there in the front. Okay, with the current I going down side 2. You can see it right there. Because we're looking, it's right there, that shorter front side of the loop. There is a magnetic force on it. You can think about what direction that is, but I will contend that for the axis of rotation, which is coming straight out of the screen towards us, the force F2 produces no torque. It has no moment arm. Notice that side 4, by the way, in this kind of drawing, is not visible. It's at the back. You can't see that. It's hidden by the front. But it also would have a magnetic force, but that would also produce no torque because it had no moment arm for the axis of rotation. Then let's look at side 3, which is down here at the bottom. And it has current I and an L vector that is directed into the screen. And you do I times L cross B, the B is to the right, and you get a magnetic force vertically downward, labeled F3. Okay? All right, now here's the contention, and these little curved orange arrows are trying to convey this next fact. Both forces F1 and F3 that are shown would produce counterclockwise rotation about the axis. F1 pointing up this way, F3 pointing down this way on this rigid frame with an axis going through the middle and perpendicular to the screen. They would produce counterclockwise rotation about that axis. They would produce a net torque. And we're going to calculate that torque by remembering one key expression for torque from last semester. We already see the direction is counterclockwise. That'll be a positive torque. The magnitude of the torque is calculated by force times moment arm. Hopefully that rings a little bit of a bell. Force magnitude times moment arm. Moment arm is a distance. It is the perpendicular distance from the axis of rotation to the line of action of the force. Let's apply that idea. Let's focus specifically on the torque resulting from the force F1 on side 1. So here's a reduced image. We're just honing in on the key parts. And you are seeing, on edge, of course, side number 1, right there, with the current coming out of the screen towards us, and half of length 2, down from the top there to where the axis of rotation is. Which is right there. Okay? So that length of that black line I just drew is little b over 2, since the length of the short side is little b. There's the normal unit vector for the loop. As before, up and to our right, n hat. There's the direction of the magnetic field, vector b arrow. So theta is the angle between n hat and b arrow. And let's start talking about the torque from that force. I'll start over here. We'll label it tau 1, the torque from the force acting on side 1. That'll be the magnitude of the force, F1, times the moment arm that goes with it, R1 perp. Okay? And that moment arm is highlighted here in this drawing. It's right here, because there's the line of action for F1. Just extend F1. That's the line of action. And the moment arm is, once again, the perpendicular distance from the axis of rotation to the line of action. Right there. Okay? So let me draw it in red, just to be clear. It's right there. That's the moment arm, R1 perp. And I contend in this little right triangle up above that this angle at the top is our theta, same theta as over there on the right. So when I express this moment arm, that length of that red side of that right triangle, it's just hypotenuse times sine theta. And hypotenuse is the distance little b over 2. So little b over 2 sine theta. But what is the magnitude of that force on side 1? We've got to figure expression out for that. Well, that's a magnetic force on a current carrying wire, so that'll be I times what I will call L1 cross B. That's our go-to. And let me come down here right below and draw. There's the L1. You see that for side 1? It's coming straight out of the screen towards us. And the B is due right, capital B, arrow. No, so what's the angle between L1 and B? Watch out, because there's another angle floating around in this picture, isn't there? A theta. And so there's a temptation just to latch on to whatever angle there is in the picture. But that's not what I need for F1. To do that vector product there for F1, I need the angle between L1 arrow and B arrow. And I think my picture down here clearly shows that that angle is 90 degrees, not theta. So the magnitude of F1 would be I times the magnitude of L1, magnitude of capital B, sine of 90 degrees. Sine of 90 degrees is plus 1. So this is I. Magnitude of L1 is the length of side 1, though that's a long side. That length is little a. That's what we called it. And then that symbol for the magnitude of the magnetic field. That's the magnitude of the force. So now let's put that in our torque expression, tau 1. Little I, little a, big B, little b over 2, sine theta. That's where the theta comes in. Okay? That's the torque, about the axis of rotation due to the force F1. Here's a key result. I want you to make sure you understand this for yourself. you get the same torque expression exactly the same from the force F3. Okay? Not the opposite, exactly the same from the torque F3. F3 is the force on side 3, as we showed in the earlier picture. So then what is the net? Of course, that's what we want, right? The net torque on the loop about the axis of rotation. I'll call it tau loop. Well, it's this result for the torque from side 1 multiplied by 2. From side 3, I get another contribution, same. So that becomes then little I, I'm going to write it like this, times little a times little b times capital B times sine theta. Do you understand what all the symbols mean? Of course, I is the current in the loop, little a is the length of the long side, little b is the length of the short side, big B is the magnitude of the magnetic field from the magnet, and sine of theta, where theta is the angle between the n hat and the b. But notice something. The combination of little a times little b, well, that's just the length of the long side times the length of the short side of this rectangular loop. That's the area inside the loop. Let's just call that capital A. Yeah? So then the expression for the net torque on the loop is current I, area inside loop, magnetic field from the magnet B, sine theta. Okay? All right, so that's basically our key result. We're just going to make it prettier now. All right, so here's the result for a single loop of area A carrying current I. The torque on the loop is I times area times field times sine of angle between n hat and B. Now, if we're really going to make an electric motor with one of these loops with wire on some kind of a frame and an axis, it turns out that what you really want to do when you wrap that wire around that rectangular frame is wrap it around multiple times. Because then you get a multiplicative effect. For every time you wrap the wire around, and every wrapping, called a winding, okay, or it's also called a turn, every time the wire goes around the frame of this loop once, you get an extra winding or turn, you get this expression for the torque, I, A, B sine theta, for every time the wire goes around, if you wrap the wire around multiple times. And if you get a multiplicative effect, you can get a bigger torque on the thing. So you wrap the wire around the frame multiple times. And the result is then called a coil, okay? Which is just capital N windings or turns, capital N loops, each having area A and current I. And you just get a multiplicative effect. And then the torque on this coil that you have made is capital N I A B sine theta. Okay? Then that capital N is a biggie. That's the multiplicative effect. Okay? Note, by the way, that the stuff I've put in the parentheses, I did that on purpose. Because those three things, number of windings of the wire around, the current in each winding, and the area, those are all properties of the coil. Properties of the coil. B is a property of the magnet, which is a separate thing. Okay? And I'm going to talk, that's an important point now, because I'm going to show you with one more section in chapter 28 how to combine what we've got here for the torque on the coil with one more idea. So now I'm talking about chapter 28, section 8, where we're going to introduce the concept of a magnetic dipole. Reminder, we talked earlier this semester about an electric dipole, which consisted of two electric poles, a positive charge and a negative charge. And that electric dipole had an electric dipole moment, little p, arrow. Okay? And now we're going to have the magnetic version of that. We're going to have a structure, a device called a magnetic dipole. And in its simplest manifestation, a magnetic dipole is any current-carrying loop. Okay? Any current-carrying loop is a magnetic dipole. And so this simple-looking drawing shows in blue, kind of in a circular shape, a current-carrying loop. Right? That blue there is supposed to represent wire, for example. And it's been wound around in a circle, and we've hooked up the ends to a battery or power supply so that there's current. Conventional current is flowing counterclockwise when viewed from above. And that's a magnetic dipole. Okay? And every magnetic dipole has a corresponding magnetic dipole moment. Just like every electric dipole has an electric dipole moment. And the definition of electric dipole moment, first of all, it's a vector, p arrow, and so it has a magnitude and a direction. And for the electric dipole moment, the magnitude is the magnitude of either charge, because they have equal magnitudes, times the distance between them. Direction, by definition, was away from the negative charge towards the positive charge. Now that was just the definition of electric dipole moment. Now I'm going to give you the definition of magnetic dipole moment. Okay? And the symbol for it. Remember, the symbol for electric dipole moment was little p arrow. The symbol for magnetic dipole moment is completely different. It's a lowercase Greek letter mu, arrow, because it's a vector. Okay? All right, here's its definition then. It's both written here and below. Okay? By the way, I'm assuming this wire has N windings, and the area inside is A, and the current going around each winding is I. Okay? So here's the definition of magnetic dipole moment. Mu arrow. It's number of windings N, current in each winding, I, area inside, A, that's the magnitude, and then to get the direction, a normal unit vector, n hat, where n hat is normal to the perpendicular to the plane of the loop, and using the modified right-hand rule. Namely, reach in with the fingers of your right hand and wrap them around the loop the way the current is going, and stick your thumb. That's the direction of mu. That's the direction of n hat, which is the direction of mu. And that's how they get this drawing, this direction right here, for the magnetic dipole moment vector for that loop. Okay? Now with that definition, go back up and look up above for the expression for the total magnetic torque on a coil carrying current. And the thing inside the parentheses is the magnitude of this new thing we just called the magnetic dipole moment, right? Right here. That's the magnitude of mu. Of course, this thing right here is the magnitude of B. And then that's the sign of the angle between n hat and B. But n hat's the same as the direction of mu. So guess what? Here's our final expression for the magnetic torque on a loop, which includes a coil, in an external magnetic field. There it is. Tau arrow equals mu arrow cross B. Vector product of the magnetic dipole moment cross magnetic field that it's in. Notice then that the way to get the magnitude of the torque would be take the magnitude of the magnetic dipole moment times the magnitude of the magnetic field times the sine of the angle between mu and B, which is what we're calling theta. And then to get to the direction of the torque, just do the right-hand rule for mu cross B. So here's a little practice question. What angle theta between mu arrow and the external magnetic field B arrow results in the largest possible torque magnitude? Think about that a minute. Feel free to pause if you need to, but do come up with an answer. All right, well, all you got to do is look at this expression right here for the torque magnitude. We're asking what theta, what angle between mu and B gives you the largest torque magnitude, right? Did you say that you need a theta of 90 degrees, just based on the fact that you've got sine theta? That would be a situation where, if the mu was directed like that, then the B that it's in would be like that, perpendicular to each other. That's when you get the biggest torque on your coil/loop. Here's another practice question. What angle between mu arrow and the external magnetic field, B arrow, results in the smallest possible torque magnitude? So get an answer. Did you say two answers here? Theta could be 0 or 180. So 0 would mean the mu would be, for example, like that, and the B would be also like that. There is no torque on a magnetic dipole oriented like that. There is also no torque, 0 torque, on a magnetic dipole with magnetic dipole moment oriented exactly opposite to B, like that. So those will give you the minimum torque magnitude, namely 0. Okay? I will just remind you for the electric case, meaning an electric dipole with an electric dipole moment P arrow in an external electric field, E arrow, the torque on that dipole was P cross E. Electric dipole moment crossed electric field. And for the magnetic version of that, a magnetic dipole in a magnetic field, the torque is mu cross B. Also, like in the electric case, in the magnetic case, there is an energy stored in the orientation of the magnetic dipole to the external magnetic field. There's stored energy, potential energy, U. And the formula for it I'm just going to state, negative mu dot B. It comes from the simple fact that if you start out with a magnetic dipole moment, red pen, and an external magnetic field, green pen, in the same direction, and leave it like that, the magnetic dipole, which is just a loop on an axis, would stay there because there's no torque. And if I wanted any other configuration other than this, I'm going to have to do work to rotate the dipole away from that 0 torque configuration. I have to do work to rotate the dipole away from that. And that's where there's stored energy. Just like I have to do work to stretch a spring. Okay? And that's the formula then. Let's look at it. Negative mu dot B. Watch out, dot, scalar product. And watch out for the negative sign. I will just remind you that in the electric case, if you start out in the electric case with the electric dipole aligned with the electric field so that there's no torque, and you want any other configuration, you're going to have to do work to rotate that electric dipole. So again, there's stored energy. And in the electric case, that's given by negative P dot E. That's the electric version. Now we have the magnetic version. And these pictures down here show the extreme energy orientations of a dipole in an external field. Here on the right is the lowest energy. The dipole with its current loop has its magnetic moment, mu arrow, in the same direction as B. then the formula for U would be negative magnitude B, magnitude mu, magnitude B. Now that's a dot there, so it would be cosine of the angle between mu and B, which is 0. And the cosine of 0 is positive 1, so this is just negative magnitude mu, magnitude B. That's the lowest possible energy. The highest possible energy configuration is here, with the dipole twisted around so that the magnetic dipole moment is exactly opposite to the external field. And now the energy is negative mu dot B, so negative mu magnitude times B magnitude, and now we're taking the cosine of 180 degrees. And whereas the cosine of 0 degrees is plus 1, the cosine of 180 degrees is negative 1. And so the energy is plus mu times B. And that's the highest possible energy configuration of a magnetic dipole in an external magnetic field. Okay, so I will just leave you with a little bit of practice for class engagement. Very similar to something we talked about in the electrical case with an electric dipole in an electric field. Now we have a magnetic dipole in a magnetic field. The magnetic field, B, is pointing to our right in the plane of the screen. And we have 4 orientations of a magnetic dipole moment, mu, in this uniform magnetic field B. 1, 2, 3, 4. And there's this angle phi to help us think about the directions. And the phi is the same size in all 4 cases. Part A. Rank these 4 orientations according to the magnitude of the torque on the dipole, greatest to smallest. Okay? Magnitude of torque. B. For each of the orientations, state the direction of the torque on the dipole. And your options are either into the screen or out of the screen. Think about mu cross B in the right-hand rule. And then for C, rank the orientations according to the magnetic energy, the U, most positive first to most negative last. Okay, so just a little bit of practice with a magnetic dipole in a magnetic field. And then we'll be having a class video where we'll be practicing with these same ideas. And that's all for this video.